Somewhere in your garage, or your trunk, or a kitchen drawer, there might be a small block of plastic about the size of a thick paperback book. It doesn't look like much. Some of them cost less than a decent pair of headphones. You can find ones in that $40 range at pretty much any auto parts store or online. And that little block can take a completely dead car. I mean dead, dash lights off, nothing, not even a click, and get the engine running in under 10 seconds. No other car. No jumper cables snaking between two vehicles in a parking lot. No flagging down a stranger and hoping they know what they're doing with a pair of alligator clips. So here's the question worth actually answering. How does something that fits in a glove compartment produce enough electrical punch to turn over a multi-ton engine? Because if you've ever tried to jump a car the old-fashioned way, you know it takes real power to do that. A car engine at rest has a lot of mechanical resistance to overcome just to get the pistons moving. So where's all that force coming from? Packed into something roughly the size of a phone. Let's actually open this thing up, conceptually, and look at what's inside. And along the way, let's also talk about why the old method, the two cars and a set of jumper cables, has been quietly falling out of favor, because understanding what's wrong with the old way makes it a lot clearer why this new way is such a genuine upgrade. Let's talk about why your car battery died in the first place, because understanding that actually explains why the fix works so well. Most dead car batteries aren't actually destroyed, they're just depleted. Maybe you left the interior lights on overnight. Maybe it's the middle of winter, and the cold slowed down the chemical reaction inside the battery to the point where it just can't deliver enough current. Maybe the battery's a few years old and its capacity has quietly degraded without you noticing until this exact moment. In almost all of these cases, the battery itself is fine. It just doesn't have enough stored energy left to spin the starter motor. All it needs is a temporary boost of current, just for a few seconds, to get things moving. Once the engine catches and starts running, the alternator takes over completely and starts recharging the battery on its own. The jump starter's entire job is to bridge that one small gap. Let's actually talk about the traditional method for a second, because it's worth understanding exactly what it demands of you before we get into why the battery pack is such a leap forward. Jumping a car with cables requires finding a second, running vehicle. It requires parking that vehicle close enough that the cables can reach, but not so close that the two cars are touching. It requires connecting 4 separate clamp points in a very specific order: red to the dead battery's positive terminal, red to the donor battery's positive terminal, black to the donor battery's negative terminal, and finally black to an unpainted metal surface on the dead car, deliberately avoiding its own negative terminal. That last detail matters more than people realize. Batteries can vent small amounts of hydrogen gas, especially older ones, and a spark occurring directly at the terminal carries a real, if small, risk of igniting that gas, grounding the final connection somewhere else on the engine block, or a metal bracket, moves that spark safely away from the battery itself. And if you get that order wrong, even slightly, the consequences aren't hypothetical. Reversing polarity, meaning connecting positive to negative or vice versa, can send current flowing the wrong direction through a car's electrical system, and modern vehicles are absolutely loaded with sensitive computer modules that do not appreciate that kind of surprise. People have melted clamps, blown fuses, and in some documented cases, fried an alternator entirely by getting this sequence wrong under the stress and poor lighting of an actual roadside emergency. None of this makes cable jumping impossible or even particularly dangerous when done carefully and correctly. But it does mean the traditional method has a real skill floor. You need to remember the sequence, under pressure, in the dark, possibly in the rain, and you need a second working car to even attempt it in the first place. If you're stuck in an empty parking lot at midnight with nobody around, none of that matters, because step one of the whole process simply isn't available to you. This is exactly the gap a self-contained jump starter closes. It doesn't need a donor vehicle. It doesn't need another driver standing there. It's already got its own power source built in, sitting fully charged and ready. And all it needs from you is 2 connections instead of 4. So let's actually get into what's inside that little block. Inside that little battery pack isn't some exotic new technology, it's lithium-ion cells, the same basic battery chemistry sitting inside your smartphone, your laptop, and increasingly, electric vehicles themselves. But there's a critical difference between the lithium cells in your phone and the lithium cells in a jump starter, and it comes down to one thing: discharge rate. Your phone battery is built to deliver a small, steady trickle of power over many hours. If you tried to yank hundreds of amps out of a phone battery all at once, the protection circuitry would shut it down immediately, because that's not what it's designed for, and doing so could genuinely damage or overheat the cell. A jump starter uses different cells entirely. High-discharge lithium cells, specifically engineered to release an enormous burst of current in a very short window, then essentially rest. It's less like a marathon runner and more like a sprinter that only needs to run for about 10 seconds at a time. This is where you'll start seeing 2 specific numbers on the packaging of any jump starter: peak amps and cranking amps. Peak amps is the maximum instantaneous current the device can theoretically push out, often measured in the 1 to 2000 amp range, sometimes higher, but only for a few milliseconds at a time. Cranking amps is the more meaningful number for real-world use. It's how much current the unit can sustain continuously for several seconds, which is actually what's needed to keep a starter motor spinning long enough for the engine to catch. A typical gas sedan generally needs somewhere around 400 to 600 cranking amps to fire up reliably. Bigger engines, especially V8s and diesels, need considerably more, sometimes well over 1,000 for a large diesel truck engine. This is exactly why manufacturers list a specific maximum engine displacement, usually in liters, that a given unit is rated to handle. A small compact jump starter built for 4-cylinder sedans genuinely may not have the sustained output to reliably crank a big diesel pickup. So, how does a battery pack barely bigger than a smartphone generate that much current without melting internally? This is the part most people never think about, but it comes down to internal resistance. Every battery has some amount of electrical resistance inside it, and that resistance is what generates heat and limits how fast current can flow. High-discharge lithium cells are built with much lower internal resistance than standard consumer-grade lithium cells, using thicker electrode materials and different manufacturing techniques specifically optimized to let current flow rapidly, without much energy loss as heat. It's essentially a battery built for controlled, short, intense output rather than smooth, sustained output. Once that current leaves the battery cells, it doesn't go straight out through the clamps unregulated. There's a boost converter circuit sitting between the battery and the output cables, and its job is to keep the voltage stable and consistent even as the internal battery's own voltage naturally sags a bit during a high current discharge. Without that circuit, the power delivered to your car's electrical system could spike or dip unpredictably, which is exactly the kind of thing that can damage sensitive onboard electronics in a modern vehicle. And remember, today's cars are absolutely packed with computers, sensors, and control modules that are a lot more delicate than the ignition systems of decades past. And that brings us to the safety systems, because this is genuinely one of the most underrated parts of how far this technology has come. Jumping a car the traditional way, with cables and another vehicle, has always carried real risk. Connect the clamps in the wrong order, or reverse the polarity, and you can cause sparking, blow a fuse, or in worst cases damage a car's electrical system entirely. Modern lithium jump starters build multiple layers of protection directly into the device. Reverse polarity protection means that if you accidentally connect the clamps backwards, the unit simply won't send power through. Full stop, no spark, no damage, it just won't activate. Short circuit protection instantly cuts current if the clamps accidentally touch each other. Many units also use spark-proof clamp technology, meaning the connection point itself is engineered specifically to avoid generating a spark even during connection, which matters because a spark near a battery, especially an older lead-acid battery that might be venting a small amount of hydrogen gas, is a genuine safety concern. Overcurrent, shutdown, and thermal protection round things out, cutting power automatically if anything draws more current than it should, or if internal temperatures climb too high. It's worth saying clearly, though, that these built-in protections are a safety net, not a replacement for paying attention. Even with reverse polarity protection, the responsible habit is still to double-check the red and black markings before you connect anything every single time, rather than assuming the electronics will always catch a mistake. Most manufacturers will tell you the same thing directly in their manuals. The protection circuitry exists to prevent damage if a mistake slips through, not to make carelessness risk-free. Here's a detail that genuinely surprised a lot of people when this technology first went mainstream: cold weather performance. Car batteries famously struggle in freezing temperatures, which is exactly when you're most likely to need a jump in the first place. Nobody's battery dies on a warm, easy afternoon. It's always the coldest morning of the year. But here's the catch. Lithium-ion cells themselves also lose a meaningful chunk of their capacity in freezing conditions, sometimes losing 20 to 40% of their rated output once you drop below freezing. This is actually why some of the more advanced units on the market now include what's sometimes marketed as preheat technology, where the device briefly warms its own internal cells for a few seconds before discharging, specifically to counteract that cold weather capacity loss and make sure it can still deliver its full rated output even in genuinely brutal winter conditions, in some cases down to -40 degrees. Now let's talk about why this thing can sit in your trunk for months, forgotten, buried under a snow brush and an old gym bag, and still work when you finally need it. This comes down to something called self-discharge rate, and it's actually one of the biggest advantages lithium has over the old lead-acid jump starter packs that used to be the only option. Lead-acid batteries lose charge fairly quickly, just sitting unused, which is why older jump starter packs needed to be plugged in and topped off constantly, almost like a habit you had to maintain. Or you'd go to use it in an emergency and discover it was completely flat too. Lithium cells discharge far more slowly when idle. Many modern lithium jump starters can sit fully charged for several months, in some cases closer to a year, and still retain the majority of their stored charge. That's a genuinely huge practical difference, because a safety device that requires constant maintenance to actually work when you need it isn't a very good safety device. There's also a size and weight story here that's easy to take for granted. Older jump starter packs, the lead-acid style ones, were heavy, bulky things, genuinely the size of a small toolbox, awkward to store, annoying to carry. Lithium-ion energy density, meaning how much energy you can pack into a given size and weight, is dramatically higher than lead-acid. That's the entire reason. A device that used to weigh several pounds and take up real trunk space can now be small enough to toss in a glove compartment or a backpack without a second thought, while still delivering equal or greater cranking power. Let's actually walk through what happens, step by step, in the 10 or so seconds between you connecting this thing and your engine roaring back to life. First, with the car's ignition completely off, and any accessories like headlights, radio, or air conditioning switched off to reduce load, you clip the red clamp onto the positive terminal of your dead battery, and the black clamp onto an unpainted metal surface on the engine block or chassis. Notably, not the negative terminal itself, which is actually the safer standard practice, since it moves any potential spark further away from the battery. Once both clamps make contact, you power on the unit. Internally, the moment you turn the key or press the ignition button, the system detects the sudden current demand, and the boost converter circuit ramps the internal battery's output up almost instantly to meet it. The high-discharge lithium cells release their stored energy in a rapid burst. That current flows through the cables into your car's electrical system in parallel with your car's own weak battery, and together they supply enough combined current to spin the starter motor with real force. The engine turns over, catches, and starts running under its own combustion power. At that exact moment, your job is done. You power off the jump starter, disconnect the black clamp first, then the red one, and the vehicle's own alternator takes over from there, recharging the car's battery as you drive. It's worth letting the car actually run, or better yet drive it, for a solid 15 to 30 minutes afterward, since a single jump doesn't fully recharge a depleted battery on its own. It just gets the engine running so the charging system can finish the job. Now, it's worth pausing to bust a couple of persistent myths people carry around about these devices, because a lot of the anxiety around jump starting comes from misunderstandings rather than actual risk. Myth number 1. A jump starter will fully recharge your dead battery. It won't, and it was never designed to. Think of it strictly as a starting aid, not a charger. Its entire purpose is delivering that one short burst of current needed to get the engine turning over. From that point forward, your car's own alternator is doing all the real recharging work, which is exactly why driving afterward matters so much, more than people expect. Myth number 2. Bigger peak amp numbers always mean a better jump starter. Not necessarily. Peak amps only lasts for a few milliseconds. So a unit that boasts an enormous peak number but weak sustained cranking amps might look impressive on the box, while still struggling to actually start a larger engine. Cranking amps, and the tested performance in cold weather specifically, tell you far more about real-world reliability than the peak number alone. Myth number 3. You can attempt to jump a battery that's cracked, bulging, leaking, or frozen. You genuinely cannot safely. A damaged battery case can mean internal damage that makes it prone to venting more aggressively or even rupturing under the stress of a jump attempt, and a frozen battery, in particular, carries a real risk of the internal plates cracking. If a battery looks physically damaged in any way, the correct move is replacement, not a jump. Let's also talk briefly about what actually causes these devices to fail or underperform when people expect them to work and they don't, because knowing the common failure points helps you avoid them. The single biggest complaint people run into is discovering the unit itself was never charged, or was charged so long ago that it had quietly drained down more than expected, which is exactly why it's worth doing a quick top-off charge every couple of months, even with lithium's slow self-discharge, just as a habit rather than a strict necessity. The second most common issue is loose or corroded connections at the battery terminals themselves. A jump starter can be perfectly functional and still fail to start a car if the clamps aren't making solid contact with clean metal, so a quick, wire brush cleaning of visibly corroded terminals before attempting a jump can make a real difference. And the third is simply mismatched capability. Attempting to start a large diesel engine with a jump starter rated for compact gas engines, which will typically trigger the unit's own overload protection rather than actually damaging anything, but it will leave you standing there confused about why nothing's happening. It's also worth being honest about what you should look for if you're actually shopping for one of these, since not all of them are built equally. Beyond the peak and cranking amp figures, pay attention to how the unit performs specifically in cold weather testing rather than just room temperature specs, since that's the condition you're most likely to actually need it in. Check what the battery capacity is rated in watt-hours, since higher capacity generally translates to more jump attempts on a single charge, sometimes 20 to 40 jumps before needing a recharge. Confirm the safety features explicitly. Reverse polarity protection, spark-proof clamps, short circuit and thermal protection should all be standard at this point, and if a listing doesn't mention them, that's worth noticing. And pay attention to build quality on the clamps themselves. Cheap, thin spring clamps with weak grip can fail to make solid contact with a battery terminal, even when the electronics inside the unit are perfectly capable, which defeats the whole purpose. One more thing worth knowing, especially if you're the type who likes to actually understand the tool sitting in your trunk. Most of these units aren't purely single-purpose anymore, because they already contain a rechargeable lithium battery and some clever power management circuitry. Manufacturers have leaned into turning them into small multi-tool devices. It's common now to find a jump starter that also works as a USB power bank for charging a phone during a roadside wait, includes a built-in LED flashlight with a strobe or SOS mode for visibility at night, and in some higher-end models, even an integrated air compressor for topping off a low tire. None of that changes the core jump-starting technology we just walked through. But it does explain why these little blocks have become such a fixture in emergency kits, rather than a one-trick gadget people forget about after a single use. Stepping back, what you're actually holding, in that unassuming little block, is a fairly elegant piece of engineering. High-discharge lithium cells built specifically for short, intense output. A boost converter keeping that output stable under load. Multiple layers of electronic protection, quietly working in the background to prevent the exact kinds of mistakes that used to make old-school jump-starting a genuinely risky, second-car-dependent process, and an energy density high enough to shrink what used to be a heavy toolbox down to something that fits in a coat pocket. It's one of those quiet, unglamorous pieces of consumer technology that most people never think about until the one morning they desperately need it. And then, suddenly, it's the most impressive $40 they've ever spent. If you found this breakdown useful, there are plenty of other everyday devices hiding genuinely clever engineering behind a boring-looking exterior, and I'll keep digging into them. Subscribe if you want to see what gets torn apart next.